Rector, ladies and gentlemen, welcome to the defense of my PhD thesis. And the next few minutes I would like to give you a brief introduction to my research. And I actually want to start with the word single complexes, because that is my fascination, the dynamics of single molecules in the microworld. That's why I started a PhD, and it's so different from our environment, which is governed by gravitation and inertia. So just to give you a brief impression of that, if you like the approach also holds true in the photosynthesis, but there it's even more interesting because we can also look at the interaction with light. And so on the top left you have a leaf. If we zoom in on the subcellular level, you get the chloroplasts. And in there you have the thylakoid membranes, stacked membranes, and in there the photosynthetic machinery is located. On the top right you see then the thylakoid membrane. That's the location of the first steps of photosynthesis, so it's called the light reactions. So there the light is absorbed and then turned to chemical energy via charge separation and electron transport and the buildup of a proton gradient. I was actually looking at photosystem 2 here. That's a sub-part of it, and in the center you see a reaction center, so that's where the photochemistry happens, and all around it is surrounded by so-called antenna complexes, light harvesting antenna complexes, and as the word says, it's all about absorbing as much light as possible, like an antenna. And this energy is then transferred to the reaction center where it can be used for photochemistry. And here you see an example of a light harvesting complex. It's fully packed with pigments, and pigments are actually the molecules which really do the interaction with light and absorb the light. And apart from the main function to absorb light, antenna complexes also have the important function in case there's too much light. They can actually dissipate some energy, and this is used for a mechanism in photoprotection, so to protect the reaction center from overexcitation. And that's this dual function of, on the one side, light harvesting but photoprotection. On the other side, I was looking at this. And I had different projects. One was really looking in detail at the photophysics of the main antenna, the stromeric antenna in detergent. But I was also looking what happens if you change the environment. So I was looking at the native thylakoid environment, but also a more artificial system, the liposome system. And there, the advantage of that is you can also look at what's happening if you have interaction between multiple complexes. And finally, also in a functional environment, so if you not only have an isolated antenna, but you put it in a functional photosystem too. And I want to give you two examples. Of course, I have to also explain the technique. And that was single molecule fluorescence spectroscopy, my favorite. And to do that, so you put your complexes in a very high dilution on a surface, they bind to it. And then when you're in the microscope, you illuminate it with a laser, and then you make an image. And down here, you see then the raster scanning of the laser, which builds up the image, and all these bright spots now represent the single proteins. And the nice thing, if you do scanning, you can go to a single one, and then you can follow really the light coming out of the single complex. On the top right, you see now a video playing. That is what I meant with this dynamic. So you see it turned off, and the color of this emission is changing. That's what we call the fluorescence spectrum, and below is we also look at the brightness of the light which is coming out, and you see also in real time, so on a second time scale it's changing a lot, sometimes turning off, but also in a millisecond time scale there are some changes, and you can go even deeper. On a microsecond time scale you have changes of the electronic properties of pigments. On an even faster, so a billionth and trillionth part of a second, you also really look into how long does energy actually stay on a single pigment. And so one example is now singlet-triplet annihilation. Singlet and triplet, these are two just electronic configurations in a pigment. And I was looking at that to look at the fluorescence lifetime. So the red curve on the left here shows, let's say, how long energy is usually stored on a protein in the nanosecond range. But the blue one, if you illuminate it a lot, you see that the signal is dropping very rapidly in the beginning. And that is because there is another mechanism, indeed singlet-triplet annihilation, which takes out this additional energy. And I also came up with a method to measure that directly, so that you see on the right. And it's basically just turning on and off the laser, and when the laser is off, this triplet states, they went away, and in the beginning of when the laser is turned on, you have maximum signal, and then the signal drops because you accumulate this second quenching triplet state. And with that, I could really nicely illustrate it, and we did some modeling with it as well. And the connection to photoprotection is that lifetime in itself is a quite important parameter, because with that you know how fast the energy goes away, and that if the energy is already going fast away in the antenna, it protects the reaction center from too much energy. And then the second I want to show you is now dynamic quenching in a photosystem 2. So again, on the top right, you see what's happening in an isolated antenna, this blinking. So this is really what the fluorescence intensity is that's turned on and off. But if you look at the whole photosystem 2 on the left, you also see some kind of reminding kinetics like this, so it's still going up and down. But if you look at the lifetime on the bottom left, you see that the blue one is much shorter than the black one, so it's quenched. And we think that the explanation is that because here in a photosystem 2, you have all these subunits, and all of these subunits can do blinking basically, and if you sum that up and you see the superposition, it's quite likely that one of them is quenched, and that's what's happening. But the nice thing is also that we, again with the same modulation technique I showed you before, I can also look at the accumulation of this quenched states. And the nice thing about it is that it's light intensity dependent. So if I turn on the light, it seems that these quenched states are accumulated. And this could very well also be used in native light harvesting if this effect is made a bit stronger and works together with other, for example, aggregation or other proteins. This is indeed how it could work. And then with that, I would like to just give some key summaries. So I was looking at the fluorescence kinetics and also developed the tools for that in a time range from picoseconds to seconds. And the outcome was that we had, I think, a really nice quantitative description of single triplet annihilation. So that's the detailed kinetics. The experiments on the lipid environment resulted in the main light harvesting capacity is still retained in the lipid, so it's not intrinsically quenched. But if you go in the liposomes, then the interaction between complexes does indeed quench. And finally, that the light intensity dependent accumulation and decay of quenched antenna, that's really visible also in photosystem 2, and is a nice connection to photoprotection in native light harvesting. And with that, I would like to thank you for your attention.